All right, I'm back. So Planck's constant in SI units this is on that table of information that the AP folks give you. 6.63 times 10 to the negative 34 joule seconds. 6.63 times 10 to the negative 34 joule seconds. Again, you don't need to memorize that. You just need to know how to use it. So that's, and it's a true constant. It's a true constant. Now, to calculate the energy of a specific bundle of, that's what we call a photon, a specific bundle of electromagnetic energy, you need to know Planck's constant. You need to know the frequency of that wave. So let's use, for example, yellow light, which is 5.09 times 10 to the 14. That's just one of the few I can remember. So that's going to be 6.63 times 10 to the negative 34 times 5.09 times 10 to the 14 hertz. Again, this is yellow light. I just happen to have that one memorized. And then you calculate that out. Let me go grab my calculator because I am unprepared. And you know, your answer is going to come out to be joules because this is in joules second, that, and this is in hertz. And a hertz, remember, is actually 1 over seconds. That's what a hertz is. So we do this, so 6.63 times 10 to the negative 34 times 5.09 times 10 to the 14 equals 3.37 times 10 to the negative 19. So 3.37 times 10 to the negative 19 joules. Okay, that's in SI units. Now, in the world of atomic physics, we more often than not do not deal with joules. We deal with a different energy, and that's called a different energy unit called electron volts. Well, what is an electron volt? You know that that potential energy, all right? Well, you know that voltage is defined as potential energy, electric potential energy per unit charge, all right? Well, let's talk about not just any old charge, but specifically the elementary charge E, all right? The charge on an electron or a proton, right? Negative electron, positive proton. So if we're talking about that, the potential difference due to the elementary charge, it would be, oopsies, delta U all over E. Okay? So delta U equals E delta V. And when you multiply E, which again is the elementary charge, 1.6 times 10 to the negative 19 coulombs, times delta V, then whatever that is, you're going to get an energy, right? Now, an electron volt is the energy of in this case, it's going to be of a photon, the energy of something that has this charge over 1 volt of potential difference. That's its definition. It's in the textbook if you want to read it. This is chapter 27. And it's also, I might add that this is an excellent resource for this section. We're in the Quantum World, chapter 18. Okay, so an electron volt, it's just a unit, which is this charge times 1 volt. Okay, and so that, by the way, you know that's 1.6 times 10 to the negative 19 coulombs times 1 volt. So an electron volt is the same value as 1.6 times 10 to the negative 19 joules, right? 1.6 times 10 to the negative 19 coulombs times 1 volt. So that's 1.6 times 10 to the negative 19 joules. All right, so 1, in the way that we write that unit, electron volt, very common unit. Very, the most common unit in the world of small things, atomic stuff, is equal to 1.6 times 10 to the negative 19 joules. That is your conversion factor, all right? So I can convert this into electron volts. So times 1.6 times 10 to the negative 19 joules, and that's 1 electron volt. And let's see what that comes out to be. So I'm going to take that divided by 1.6 negative 19. So it comes out to be 2.1, all right? 2.1 electron volts. You can see why we like electron volts. It's much nicer to just write down the number 2.1 than to write down all this stuff with all these all the exponents and stuff, all right? But there's an easier way. Yay! There's an easier way because the kind folks at the College Board have not only given you Planck's constant as 6.63 times 10 to the negative 34, but they've also given it to you as 4.14 times 10 to the negative 15 electron volt seconds. So they've done the conversion for you. Oh, I love those people. Let's write that down. So this is 4.14 times 10 to the negative 15 electron volt seconds. Therefore, if I wanted to figure out the energy of a photon and I want to work in electron volts, then I can use this. Again, we're going to use the first part of modern physics. In fact, a whole big chunk of it, we're going to use that. The one thing I want to warn you is if you're calculating something in kilograms, if you have to go into a mass in kilograms using E equals mc squared, then you're going to go into kilograms, and then you have to be sure that you are in joules, because then that kilogram is an SI unit. So you'd have to be in here. But that's not until a little later. So let's just see what we get. So this is going to be 4.14 times 10 to the negative 15 electron volt seconds times the frequency right there for yellow light. And let's just see what we get. Like I said, 4.14 exponent negative 15, okay, times 5.09, hit the exponent key, 14. And, oh God, I love it when I get it right. It's 2.1 electron volts. 2.1 electron volts. Alrighty, I'm going to pause this, and then we're going to talk about the photoelectric effect. Ooh.